So I want to describe this next result just because it just shows how weird computational complexity results can be. Let's think about the colorability of planar graphs. In particular, here's a decision problem. We're given a graph G and a number K. Is planar graph G K colorable? And let's look at how the difficulty of the question differs as we change K. So if K is 1, what kind of graphs are K colorable? Graphs with no edges. So we can answer this question in constant time. If the number of edges is greater than 0, no. Right? As soon as there's a single edge, then you're going to need 2 colors to color the nodes in that. All right, what if it's 2? We want to know, is this graph 2 colorable? Well, you know this one already, because 2 colorability is exactly the same as testing whether the graph is bipartite. And in a previous unit, you showed that that could be solved with depth-first search, and therefore runs in big theta of n plus m. If K is 3, well, 3 colorability we showed was NP complete, but we didn't do that for planar graphs. We did that for general graphs. But it turns out that you can actually introduce another gadget into the mix here that actually lets you deal with edge crossings. So if you have a piece of the graph that looks like this and there's a crossing in it, you can actually introduce some nodes here so that the information from this node travels along and gets to this node without ever having to cross another edge, that it becomes a planar graph. I didn't explain how to do this, but it turns out to be true. So 3 coloring a planar graph isn't any easier than 3 coloring a general graph. It's NP complete. What about coloring a graph with 4 colors if it's a planar graph? Well, remarkably, the problem's gotten harder and harder, from constant to linear to basically it seems like it requires exponential time. It goes back to constant time, and that's because of the celebrated 4-color map theorem that says that any map can be colored with 4 colors. And in this particular case, any map can be translated into a planar graph, and so we know that every planar graph can be colored with 4 colors. So the constant time algorithm for this problem is just to always say yes. You give me a graph and tell me this is planar, I say, yep, it's 4 colorable. And therefore, it's also going to be 5, 6, 7 colorable because you can just use the first 4. So that's kind of cool. So one of the things to point out is that the peak of the hardness comes at k equals 3, and that actually shows up a lot in NP-complete problems. Usually if there's 2 of something that you have to choose from, the problem's pretty easy because you can try one of them, and if it doesn't work, try the other one right away. But when there's 3, you have to keep considering lots of different combinations of things, and the difficulty level really, really blows up.